All right, so welcome back, everyone. We are going to be covering backpropagation for neural networks today. And what on earth is backpropagation? Well, backpropagation is the method, propagation, that neural networks use to be able to update the theta parameters within the model. So we know that typically when we are talking about um, updating the theta parameters within our algorithms, we have something that looks like, oh, maybe theta sub j is equal to theta sub j minus alpha times the partial derivative of the cost function with respect to theta sub j. Something like that. So this alpha is just the learning rate. This is the old parameter value, and this will be the new parameter value. And so the key to updating these parameter values is that it uses the partial derivative of the cost function. So it nudges the parameters, the weights, in the correct direction as it makes its correction. So it's not finding this randomly. If it were random, it wouldn't be machine learning. It would be something else entirely. But machine learning hones in on the appropriate parameters, the appropriate weights, by using this partial derivative here. And so far, that hasn't been that bad. But neural networks add a whole layer of complexity. So, what am I talking about? Well, let's say we have an extremely simple layer where we're just going to have three nodes. So each layer, layer one, two, and three, is going to have a single node each, and they're just going to kind of feed forward like so. Okay, this one might be your input layer. So it's considered an X since it's an input. And then these two are going to be activations. Alrighty. So this is going to be my activation, and this is going to be my activation. Now I'm going to make the last layer have it be layer L, and so the layer before that would be L minus 1. Okay, so we have our input, something is happening to it, it's feeding through to the A L minus 1 layer, and then something else is happening to that, and it's feeding through to the L layer, the final node. And if I look carefully at this structure right here, um, it looks perfectly fine, except it's missing a few things. I'm missing the thetas, the weights that are going to be uh, multiplied by the activations in order to get a new value that's then sent forward. So you can imagine there's just a one here, and a one here. It's the first node. So this would be theta 1, 1 starting in layer 1. And this would be theta 1, 1 starting in layer L minus 1. Okay? Now, in addition to these, I also have the biases that I need to take into account. So, what is the bias? Well, the bias is the threshold that you need to overcome in order to have an effect. That's or the baseline, the value at which things start. What am I talking about? Well, if you look at what we've done in the past, the bias has been we've had our theta transpose x breaks down into theta 0, x 0 plus theta 1, x 1 plus, I'm trying to remember if I started at 1 or 0 typically. I cannot remember. So, unfortunately, once you code in two or three languages, you forget where the arrays start, the list. Do they start at 0, element 0? Do they start at element 1? Regardless, the very first value here, this x sub 0, this is equal to a 1, right? And so, in effect, what we have here is theta sub 0 plus theta 1 x1 plus theta 2 x2. So, this is what's called the bias because it is untethered from the actual values that are getting sent in. it is a value that kind of stands alone. So this is our bias, and I would have an, hey, hold on, let me erase that. I don't want to do it that way. Let me do it like this. I would have something like theta 0, 1 from layer 1. That would be the bias. It's going to feed in right here. And then on top of here, I would have something like theta 0 to 1 in layer L minus 1. Now, I don't need these bottom subscripts because, again, they're single notes here and it's not difficult to keep track of. But I do want to kind of focus in on this right here, this little box worth of stuff. I want to zoom in on it because this is what is happening to the very last, to determine what the very last activation is going to be. Alrighty, so what's going on here? Well, this activation is a property of the previous activation times the previous weight plus the previous bias. So I can kind of make a schematic of that as this activation here, and I'm going to drop the little subscript ones, the subscripts used all over because there's only one of them. I don't have to worry about it. It'll be obvious which one I'm talking about. So the last activation is a product of the theta of the previous weight, I should say, the previous parameter, so the L minus 1 times the previous activation, L minus 1 activation, plus the previous bias, L minus 1 bias, okay? Now, it's not exactly this because I feed whatever this value is into the sigmoid function. G is the sigmoid. So it's like what we've been doing in the past. We want to, when we've talked about this, we want to have a value that falls between a 0 and a 1. So we just feed whatever this is into the sigmoid. Now, we're going to give this a name. We're going to call this Z. Okay? And that's exactly what we've done in the past. So this is going to be Z of L because once I feed the previous weight multiplied by the previous activation and then add the previous bias, that gives me my Z, which is then worked on by the sigmoid, which maps it between a 0 and a 1, which is then assigned into the current activation, the last activation that we're looking at here. Alrighty? I know that's a lot, right? Now, now that we've got this kind of set up, let's talk a little bit about the cost function. We're going to be using mean squared error for cost. So something really simple is it's going to look like the cost function is going to equal the difference between the last activation and the y value squared. Okay? So what is this? Well, this y value is the actual value that is located inside of the training example. So it is our house price. It is whatever we're looking at. It is the actual, if we're trying to map input digits between 0 and 9, the y value is the actual digit. Was it a 5? Was it a 1? Was it a 7? This activation here says what is the likelihood that it was a 1, a 7, or a 5. So what it does is it makes a guess using this activation. It then compares that to the actual value and then squares that difference. That's going to be our cost function. So it's a simple MSE without the mean part. This is just squared error. So I guess you could call it just the SE instead of the MSE. But this is a very, very simple way to evaluate whether or not a guess is correct or accurate. Alrighty? So what happens then? Well, once it makes its prediction and then it is tested to see how well it did, it then needs to go backwards to adjust the parameters so that the next training example, it can make a new guess and you can see how well it does then with the cost function. So the difficulty with backpropagation, the reason why this is such a very complicated uh, subject to talk about is because this isn't happening linearly. This is happening for rows of nodes, columns of nodes, I should say, not rows. That would be way easier. But columns of nodes where all of these nodes are connected. And between every single one of these connections, there is a theta. There's a parameter. But there's not just the parameter, there's also a bias that goes with it. So you can see how complicated this is. In order to simplify things, turns out the math out works out just beautifully if you do it this way. When we make our final guess and then we evaluate how well we did, now we have to adjust the parameters. We have to go backwards, make changes to our theta parameters. Once we do that, we then go backwards to the next layer, adjusting the theta parameters. Once we get there, we go backwards to the next layer. And so we propagate these changes to our parameters and our biases backwards. So you have your inputs for the neural network. It goes feeds forward, makes a guess, and then it feeds all the way back, making adjustments to the theta parameters. And then it makes another guess, and then it adjusts again. And so literally, it doesn't take a large network at all for billions of calculations to be taking place with neural networks. But because we're only going to be looking one layer at a time as we work our way backward, the math isn't untenable. We can actually handle it. So, hope you're ready. We're going to have some fun with this. So, let me clear what I've got here. And let's go to the next slide. Alrighty. So, for the next slide, what we're going to do is we're going to draw that same relationship, but in a tree structure that will get a lot of mileage out of using this tree structure. So, we're going to start off, we're going to have theta L minus 1, so it's the previous weight, A, the activation, the previous one, so L minus 1, and then the bias, L minus 1, the previous bias. Okay, those are going to feed into a Z value, right? Where the Z is just the theta times the activation plus the bias. Okay, and this is the current Z right here. That is going to feed into the activation, current activation. But now this current activation here, you can also think, I'm going to kind of do a little dash line here showing that this can also be thought of as the sigmoid applied to the Z. So this activation, this AL, is really just a sigmoid applied to the ZL. Alrighty, now last but not least, we're going to have the cost. And so it doesn't feed directly into the cost. I need to introduce another variable, a y value. So it winds up looking like that. This is going to be our tree structure. The cost is determined by AL minus y, quantity squared. The AL is generated by taking the sigmoid of the Z, and the Z is generated by taking the parameter times the activation plus the bias. Okay? So when you get down to it, the things that can actually affect the cost are just three: previous weight, previous activation, previous bias. Those are the three components that can actually have an effect on the cost. Okay? I know. We're getting there. So, when we're talking about using gradient descent and updating the parameter values, we need the partial derivative, right? Well, we can't use just a normal partial derivative from the standpoint of we need to have the partial derivative of how each of the pieces, the weight, the activation, and the bias, affects the cost. So we need the partial of the cost function with respect to the weights, partial of the cost function with respect to the activation, partial of the cost function with respect to the bias. We need those partials in order to get the direction that we need to nudge the theta parameters to get a more accurate guess in the next loop. So let me show you what that looks like. It turns out it's not horrible, but it does use some calculus. If I want to find how the cost function is affected by the previous weight, L minus 1, like that. Well, what I'm going to do is set up a cascade of chain effects. So when you first started doing the chain rule in calculus, you probably saw something like this, and then it just kind of falls away and isn't used very often. But this would be how the partial affects the z, how the partial affects the z, how z is affected by the previous weight. There we go. I know I could say it right. And then this, what I want to see is how the A is affected by the Z. And then finally, how the cost is affected by the activation. Okay? So this partial derivative here is a chain of three partials. And if you kind of look at the math, if I used algebra, I thought about canceling like terms. Well, I could cancel these, and I could cancel these, and I would be left with partial of the cost with respect to the previous way, which is exactly what I want. That's 100% what I want to see. And so this is the mechanism we're going to use to be able to tease out how each of these three pieces affects the cost function. Alrighty. So let's see. I'm going to start working with some colors. I think it'll make it a lot easier. Let's see. I'm going to go with purple. Purple right here. Okay. So that right there is going to correspond to this piece right here. And then I'm going to go with a different color, F5. Y'all didn't need to know that. I'm talking about looking at how this piece affects the activation. And then finally, I'm going to go with orange for the last piece right here. How this affects the cost. Alrighty, so let's work each of these pieces out. Let's do the purple piece first. Alrighty, so let me go back. Actually, let me go to purple and we'll do the whole thing in purple to really emphasize it. So the partial, I can get this to work. The partial of z with respect to the previous weight. What does that equal? Well, it's the partial of z with respect to this. What is z? Well, that is the partial of respect theta L minus 1 of theta L minus 1 times activation L minus 1 plus bias L minus 1. And if I take the partial of this, which is my z, with respect to theta, my previous weight, what am I left with? Right. This equals the previous activation. Okay? Not too bad. Now let's tackle the blue. The blue's even easier. So where's my blue? If I look at how the activation is affected by the z. Well, this one couldn't be simpler because this is just going to be partial with respect to z of, well, this is just g of z. And the partial derivative of that is just going to be g prime of z. Turns out we don't really need that for being able to talk about what we're doing. Alrighty, final piece. Let's see how the cost is affected by the activation now. So partial of the cost with respect to the activation, well, that's going to be the partial with respect to the activation of, well, what does the cost function look like? Well, it looks like the squared error. So it is just the AL minus Y quantity squared. And so that partial derivative is just going to be 2 times AL minus Y. And that is our final piece. Alrighty. So now that we've done that work, I can go to the next slide so you can see it. If I can find it. Where's my next slide? Oh gosh, I was 2 slides back. Sorry about that. Here, that's the one I want you to see. So we have previous activation, G prime, and then this 2 times. So what I'm going to do is write that out over here. Okay, so let me do that. Partial, go back to this. I think I can squeeze it. I need to squeeze it in right here. The partial, no, I don't need it to be in orange though. I need that to be in yellow. The partial of the cost function with respect to the previous weight is equal to these 3 pieces multiplied together. If you allow me, I'm going to go ahead and erase these pieces because now that I've calculated, I don't need them. I just need to place them down here in this, and I'm going to run out of room this way if I don't. So here we go. First piece is going to be in purple. So it is just the previous activation. Just like that. Okay. Now that is multiplied by the next piece, that value, which is G prime of Z L, and then that is multiplied by the last one that we found, which is 2 times AL minus Y. Okay, that is my very first piece. This is the actual partial derivative of the cost function with respect to the previous weight. So we have one of the 3 pieces, how it affects the cost function. So we're 1/3 of the way there. Alrighty. I know that's a lot, right? Let me go now to the next slide. Okay, that's what we have. Ellie, I'm not keeping my slides up nicely. So if I go to the next slide, look at it. When I start to calculate the next piece, the contribution of the previous activation, it looks a little something like this. It is the partial of the cost with respect to the previous activation. Well, that's going to be the partial of Z with respect to the previous activation times partial of A with respect to Z, and then the partial of the cost function with respect to A. Okay? These two pieces are the same. They don't change. The only thing that changes is this very first value right here. So I'm going to highlight that in green. This little piece right here is all that's going to change. So I need this piece. So what is the partial of Z with respect to the previous activation? Well, it's the partial with respect to the previous activation of the same thing we had, right? We have theta L minus 1 times L minus 1 activation plus the bias. Okay, the partial derivative of this expression with respect to the previous activation is the previous weight. That's all that changes. So here we go. Partial of the cost function with respect to, oops, not that. That's for sure. Why is that not? I need an eraser. There we go. I guess I'll just start over. No problem. Partial of the cost function with respect to previous activation is going to equal, we're going to have the previous weight times these two pieces right here, the exact same ones, G prime Z, and then 2AL minus Y. Okay, so all that changed was this first piece, because these two were exactly the same. This is the only one that changed. Okay, so now that takes care of how the activation affects the cost function. The last piece we need to look at is how the bias affects the cost function. So the bias, I'm going to erase this right here. How does that change? Well, not too bad. I'll look at how the cost function is affected by the previous bias. Well, that's how the Z is affected by the previous bias. So just like that. And then these two pieces are again the same. So the only thing I have to worry about is that piece right there, that very first one. Alrighty. So I need to calculate this, and for that I will switch colors again. Alrighty. So what is that? Well, this is the partial with respect to the previous bias, which is of, the Z, which is again previous weight times previous activation plus previous bias. All right, the partial of this expression with respect to the bias is just 1. It's just a 1. So if I come over here, finish this up, I've got the partial of the cost function with respect to the previous bias. That is going to be, if I can get the right key, 1, that's just a 1, plain old 1, times, and then I've got the two pieces. So G prime, and then 2AL minus Y. All right. Now, that's a lot, right? I can now go, so you can see, so if we've gone through the one, that's what we have here. All righty. Now, what have we done? We've done an enormous amount of complicated math, but it looks simple because once you really break it down, it's not that bad. What we've done is we have figured out when we're trying to take the partial of the cost function in order to find the direction to nudge the parameters using gradient descent. The way that we do that is we have to look at how that cost function is affected by each of the three pieces: the previous weight, the previous activation, and the previous bias. Okay? So that's what we have down here at the bottom. And it's kind of nice that we have it this way. Once we have got all this worked out, we can use logic to see if this makes sense to us. So if I look at how does the weight affect the cost function, that depends on how big the previous activation is, because the activation gets multiplied by the weight. So when you're trying to determine what your z is, the same thing happens when I try to see how the activation affects the cost. Well, it affects it as depending on how big the previous weight is. So the weight is affected by the activation is affected by the weight. That makes perfect sense because right here, if we think about it, these two are multiplied together to give me the z. If I have an extremely small previous weight, it's not, no matter what my activation is, it's not going to affect things very much. So, and then vice versa, if it's really large, it's going to have a large effect no matter what my activation is. So it makes sense that the weight affects the cost function depending on what the activation is, and the activation affects the cost function depending on what the weight is. And since the bias is just added, it is not affected by anything else. It is straight whatever it is, that is what the effect is on the cost function. You don't have to worry about any other contributing factors. Okay. That may not seem like much, but that's a lot of things that have been condensed down to their essence. What we now have is we have the blueprint that can be used by the gradient descent algorithm in order to tell which direction to nudge the parameters. By doing all this math, we've unwrapped mathematically what's going on behind the scene with the multiple chain rules that the backpropagation requires as you head through a network. And all of this is for a single operation. This is occurring millions of times as it adjusts all the theta parameters, makes a new guess, adjusts all the theta parameters, makes a new guess. So I would imagine that one of the, the reasons this took so long to actually be useful is we've had this algorithm for decades, but implementing it, you've seen, you must have a very fast processor with lots of RAM in order to be able to handle all these calculations and keep everything in memory. So I hope you enjoyed this. This is what backpropagation needs. You need to understand the math behind the partial derivative of the cost function, and that's what this is. So now that you have that, you can kind of get an idea of how things are being changed as it propagates backward, layer by layer, and we can push forward into the very next thing in machine learning. So hope you enjoyed this, and I will see you later. Bye, everyone.